Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of gravitational fields. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics style examination questions, assess your understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Now in the right hand side section, write down any pieces of information which you find useful or any hints and tips on answering questions from the revision session. After the revision session concludes, write up these notes into a revision sheet for you to use independently. How should you be revising for A-Level AQA Physics? Well, firstly, you should be learning the key facts, so use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. Then test yourself. Use the Caboodle Knowledge Platform, the Seneca Learn Platform, the Student Knowledge Checker to quickly test your own knowledge. Finally, practice exam-style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. So the three steps of preparing for the exams are learn the key facts, testing yourself and practicing exam-style questions. So, what are the key facts concerning gravitational fields? Well, we have Newton's law of gravitation. That's the idea that gravity is a universal attractive force between all masses. Newton's law of gravitational attraction is F equals G m1 m2 over r squared, where F is the gravitational force, G is the universal gravitational constant, m1 and m2 are the mass of the objects, and r is the distance between the centres of mass. The gravitational field strength is important as a gravitational field is represented by gravitational field lines. The gravitational strength is equal to G equal F over m, and in a radial field G is equal to G big M over r squared. Now for gravitational potential, that is the potential energy per unit mass. V equals minus Gm over r, and the negative sign shows the attractive nature of gravity. The gravitational potential difference is the work done is equal to mass times by this gravitational potential difference. Now in equipotential surfaces, no work is done moving along them, and in our relationship between G and V, G is equal to minus the change in V over the change in r. So this indicates to us that the gravitational potential difference is equal to the area under a graph of G against r. Now for the orbits of planets and satellites we use Kepler's third law, which is t squared is directly proportional to r cubed for circular orbits. The escape velocity is the minimum speed needed to leave a gravitational field, and the energy of an orbited satellite is equal to the kinetic energy plus the potential energy, but the total should always be a negative because it's bound in an orbit around another object. Now to work out the kinetic energy we use a half mv squared, and for the potential energy we use minus gmm over r. Now, that tells us that potential has to be a negative energy. Now, for synchronous orbits, that is when the orbital period will equal the planet's rotation, whilst a geostationary orbit is the special case of a synchronous orbit around the equator of the planet. So let's just test our knowledge and understanding on gravitational fields. From this image, how can you tell that object 2 is experiencing a gravitational force? Pause the video now, then unpause the video when you want to go through your answer. Well, object 2 is experiencing a gravitational force as is inside the field of object 1. Next question, how can you tell that object 1 is experiencing a gravitational force? Object 1 is experiencing a gravitational force as is inside the gravitational field of object 2. What can be said about the size and the direction of the gravitational forces acting on object 1 and object 2? Well, the gravitational force experienced by each object is the same magnitude. The gravitational force experienced by each of them is moving them together. It's an attractive force. Will the acceleration experienced by each object due to being in the gravitational field be the same, and why? No. Each object will experience different acceleration, as whilst the gravitational force they experience is the same, their masses are different. Remember, acceleration is equal to resultant force over mass. Will object 2 or object 3 experience the greatest gravitational force from object 1 only, and why? Object 2 will experience the greatest gravitational force from Object 1 as it is closer to Object 1 than Object 3 is. Which object, Object 2 or Object 3, will experience the greatest gravitational force from Object 1 only, and why? Object 3 will experience the greatest gravitational force from Object 1 as it has more mass than Object 2, even though they are the same distance away from Object 1. From a field diagram, how can you determine the gravitational field strength of a gravitational field? The gravitational field strength can be represented by the density of the gravitational field lines. From a field diagram, how can you determine the direction of the gravitational field strength of a gravitational field? The gravitational field strength direction is represented by the direction of the field lines of the gravitational field. In this diagram, what object is producing the gravitational field, which we can then measure its gravitational field strength of? The gravitational field is being produced by the mass of object. In this diagram, which object is being affected by the gravitational field? The test mass is affected by the gravitational field. So in this diagram, which test mass is in a region of greater gravitational field strength, and why? Both test masses are experiencing the same gravitational field strength, as they are both the same distance away from the centres of mass in the gravitational field. The mass of object dictates the size of the gravitational field strength. Which test mass experiences the greater gravitational force, test mass 1 or test mass 2, and why? Test mass 2 will experience the greater gravitational force. This is because test mass 2 and test mass 1 are the same distance from the mass of object, yet test mass 2 has the greater mass. Where is the gravitational field strength the greatest value in the field, and why? The gravitational field strength is the greatest at the point mass. This is because the field density is the greatest here, and all the mass produced in the field is here. When is the gravitational field strength the greatest for a massive object, and why? The gravitational field strength is the greatest at the surface of the massive object. This is because it is the closest you can get in a gravitational field before there is a mass above the object producing a gravitational field in the opposite direction. So, what is the gravitational field strength at the centre of the Earth, and why? The gravitational field strength at the centre of the Earth is 0. This is because at the centre there is an equal amount of mass above and below that point. They are producing gravitational fields equal in size and opposite in direction. This gives a field strength of 0. So what is the gravitational potential at the centre of the Earth, and why? The gravitational potential at the centre of the Earth is 0. This is because at the centre there is an equal amount of mass above and below that point. They're producing a gravitational field equal in size and opposite in direction. They cancel through to give a potential of 0. When does the object have the greater magnitude of gravitational potential? Position 1 or position 2, and why? The object has the greatest magnitude of gravitational potential at position 1, as it's feeling a greater attraction due to gravity from the Earth as it's closer. When does the object have the greater value of gravitational potential, position 1 or position 2, and why? The object that has the greatest value of gravitational potential is at position 2, as the gravitational potential is always a negative value, so it is at a higher negative value at position 1 compared to position 2. Apart from at the centre of the Earth, when will the object experience no gravitational potential, and why? It will be when the object is outside of the gravitational field of the Earth, as it's no longer feeling an attraction to the Earth. Is work done to move the object from position 1 to position 2, or from position 2 to position 1, and how can you tell from the diagram? Work is done when the object moves from position 1 to position 2, as it's moving against the field lines of the gravitational field. Will object 2 or object 3 have the largest magnitude of gravitational potential from object 1 only, and why? Both objects will have the same gravitational potential as each other as they are the same distance away from the centre of object 1. Will object 2 or object 3 have the greatest magnitude of gravitational potential from object 1 only, and why? Well, both objects will have the same gravitational potential as each other, as they're the same distance away from the centre of object 1. Will object 2 or 3 have the largest magnitude of gravitational potential energy from object 1, and why? Object 3 will have the greater gravitational potential energy, as even though they have the same gravitational potential, object 3 has the greater mass, so will therefore have the greater gravitational potential energy. Is work done to move the object from position 1 to position 2, or position 2 to position 1, and how can you tell from the gravitational potential? Well, work is done when the object moves from position 1 to position 2 as it's moving between two areas of different gravitational potential. Where will the energy come from to change the gravitational potential energy store of the object as it moves? The energy comes from the kinetic energy store of the orbiting body. In which position will the object be orbiting slower, position 1 or position 2, and why? The object will be orbiting slower in position 2 as more of the total energy can be found in the gravitational potential store, not the kinetic store. Will the object carry out any work in moving from position 1 to position 2, and why? No work is carried out moving from position 1 to position 2 as it's not moving to areas of different potential. How can the Moon orbit the Earth successfully with no work being done? The Moon orbits the Earth without any work being done as it's in an orbital plane, which is a plane of equipotential. Is work needed to be done to put a satellite into orbit? How is this achieved? Yes, work is needed to be done as the satellite is moving between areas of different gravitational potential to do this. This is achieved with the use of thrusters. Is work needed to be done to keep a satellite in orbit? No work is needed to be done as the satellite moves in orbit as it will move in a plane of equipotential. Which satellite experiences the greater gravitational force from the Earth and why? Satellite 1 experiences the greater gravitational force from the Earth as there's a smaller separation between the Earth's centre of mass and its centre of mass. Which satellite is travelling at the higher orbital velocity, assuming a stable orbit? Satellite 1 is travelling at a higher orbital speed as it's experiencing a greater gravitational force. Which satellite will complete an orbit in a quicker time period and why? Satellite 1 will complete an orbit in a faster time period as it's travelling faster, so has less distance to cover in one orbit. In terms of gravitational potential, how can a satellite maintain a constant orbit? The satellite will maintain a constant orbit if it's on a sphere of equipotential. The satellite moves from position 1 to position 2. Both positions are in a circular orbital path. What happens to the total energy store of the satellite? The total energy store of the satellite remains constant. The satellite moves from position 1 to position 2. What happens to the kinetic energy store of the satellite and why? The kinetic energy store of the satellite decreases as the satellite is now moving slower. The satellite moves from position 1 to position 2. What happens to the potential energy store of the satellite and why? The potential energy store of the satellite increases as it's now closer to leaving the field. How can the potential energy store of the satellite increase as it's moving closer to the edge of the field? The potential energy store of the satellite when it leaves the field when it's at infinity is 0, so it starts off negative and becomes less negative or more positive and increases as it moves towards the edge of the field. In an elliptical orbit, what will happen to the speed of the satellite throughout its orbit. The satellite will increase in speed as it's getting closer to the Earth, and then decrease in speed as it moves away from the Earth. Let's have a look at some examination style questions for gravitational fields. A space probe is sent to investigate a previously uncharted planetary object. The scientists collect the following data. The data are measured when the probe is in freefall towards the planet. Using the data, deduce whether the object behaves as a point mass or as a significant mass distribution above the measured radius. Without further calculation, explain how you could use the graph of G against R to estimate the gravitational potential difference between 8,000 km and 2,000 km from the planet's centre. Assuming the gravitational potential at 8,000 km is minus 1.56 times 10 to the 7 joules per kilogram, estimate the potential at 2,000 km. Comment on the significance of the negative value and what this tells us about the gravitational energy. The probe moves from 8,000 km to 2,000 km. A student suggests that no energy is transferred because gravitational fields do the work automatically. Comment on this statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, if it is a point mass, then G should follow the inverse square law. So when the distance doubles, it should then quarter. Now you should compare this with other values as well, so you can look at this and the relationship holds. So the field does behave like that of a point mass. The mass is concentrated within 2,000 kilometers. Now the potential difference is the area under the G against R graph. So from the 8,000 kilometers to 2,000 kilometers, the area under the curve will give you that change in potential, gravitational potential. Now the potential is more negative closer to the mass. So therefore, if we know it's minus 1.56 times 10 to the 7 joules per kilogram at 8,000 kilometers, well then you could then divide that again by 4 because we're now going to 4 times closer, so it's minus 6.25 times 10 to the 7 joules per kilogram. Now the negative sign means that the gravitational potential is relative to 0 at infinity. So this indicates to us that we must be given energy to it to escape the gravitational field. Now, as it goes from 8,000 kilometers to 2,000 kilometers, the probe gains kinetic energy as it falls, so an energy transfer occurs. Now, the gravitational potential energy will decrease, it will convert to kinetic energy, so the field is doing work on the object, just that there's no fuel or propulsion needed. A group of aerospace engineers are evaluating the theoretical design of a space elevator, a long cable extending from the Earth's surface to a station in a geostationary orbit at 36,000 kilometers above the equator. Cargo will be lifted along the cable using electric motors rather than rockets. They use a model of the Earth where the gravitational field behaves as a radial for distances greater than 100 kilometers above the surface. Explain why the gravitational potential is a negative and why its magnitude decreases with an increasing distance from the Earth's centre. The energy required to lift a 500 kilogram cargo from the Earth's surface to the space station is estimated using gravitational potential values. The team claims that the energy is less than that required by a chemical rocket. Is this true? Then a student suggests that once the elevator reaches 36,000 kilometers, no further energy is required to keep it in place. Comment on this statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, gravitational potential is defined as 0 at infinity. A negative value shows that work must be done against the gravitational field to move the mass to infinity. As the distance increases, the gravitational attraction weakens, so the potential becomes less negative. We know that work done is equal to mass times by the gravitational potential difference, so it's only dependent on the gravitational potential difference. Now, rockets must also provide energy for kinetic motion, for fuel, and overcoming air resistance. Now, the elevator supplies only gravitational energy, so it's more efficient. So the claim is a reasonable one, provided that any losses to their surroundings, such as friction, are minimal. Now, objects in geostationary orbits must travel at a constant tangential speed, so it remains in orbit due to the balance between the gravitational force and the centripetal force. So the cable tension provides this force rather than a continual propulsion, so no energy is needed to stay in orbit, but a constant tension is. A satellite of mass 750 kilograms is to be lifted from the surface of the Earth to a low Earth orbit at a height of 300 kilometers above the surface. The radius of the Earth is 6.37 times 10 to the 6 meters per second, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. Calculate the gravitational field strength at the surface of the Earth and at a height of 300 kilometers above the surface. Determine the gravitational potential of both positions and hence calculate the energy required to move the satellite from the surface to this orbit. The launch team want to minimize fuel usage. Based on your result for part A 1.2, discuss whether the majority of the energy is spent on overcoming the Earth's gravity or achieving orbital motion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know at the surface G equals gm over r squared. Pop in our numbers and we get 9.8 newtons per kilogram. We now do the same at a height of 300 kilometers. So we now add the height of 300 kilometers to the radius of the Earth, all in meters. So we then get our answer to be 8.95 newtons per kilogram. Again, at the surface, it's V is equal to gm over r. We use our same values for r in the previous question. So we can pop it all through and we get minus 6.26 times 10 to the 7 joules per kilogram and minus 5.97 times 10 to the 7 joules per kilogram. So our work done is our mass times by our change in gravitational potential, which is 2.18 times 10 to the 7 joules. So this tells us that the energy required to lift a satellite is 2.18 times 10 to the 7 joules. But the orbital kinetic energy at 300 kilometers is much higher. It's about 2.5 times 10 to the 9 joules. So therefore, most of the energy is required for achieving orbital velocity, not lifting it against gravity. A newly discovered exoplanet called Trion has a moon named Lyraea. Astronomers observe that Lyraea maintains a stable circular orbit at a radius of 5.6 times 10 to the 7 meters from the center of Trion. The orbital period of Lyra is measured to be 2 times 10 to the 5 seconds. So, calculate the mass of the planet Trion, determine the orbital speed of the moon Lyraea, and calculate the total mechanical energy of the moon in its orbit, assuming its mass to be 1.5 times 10 to the 16 kilograms. Another moon, Lysara, is discovered to orbit Trion with an orbital period of 5 times 10 to the 5 seconds. Use your result from A 1.1 without further calculation to deduce whether Lysara orbits closer or further from the planet than Lyraea. Explain your reasoning. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we can rearrange the equation which comes with Kepler's third law of orbital motion to say m is equal to 4 pi squared r cubed over gt squared. Pop in all the values, and what you work it through is m is equal to 3.09 times 10 to the 24 kilograms. We know that v is equal to 2 pi over t. So when we work this all through, when we work out our value, we get it to be 1.76 times 10 to the 3 meters per second. Now we know the kinetic energy is going to be half mv squared, which is working it all through to be 2.33 times 10 to the 22 joules. We know that the gravitational potential energy is minus gmm over r, so we get that to be minus 4.66 times 10 to the 22 joules. We add the two total together and we get minus 2.33 times 10 to the 22 joules. Now, we know from Kepler's law that t squared is directly proportional to r cubed. So we know that the t of Lysara is greater than the t of Lyraea. So that indicates to us that the radius of orbit for Lysara must be greater than the radius of orbit for Lyraea. So this tells us that Lysara orbits further away. So the longer orbital period has led from our larger orbital radius. A satellite engineering firm is tasked with selecting an orbit type for a new disaster monitoring satellite. The satellite must provide regular, high-resolution imaging of all regions of the Earth, operate with minimal launch and maintenance costs, support real-time communications in emergencies. Now the firm compares 3 different orbit types. Using the table, explain the relationships between the orbital radius and the period. What does this suggest about the nature of the gravitational force acting on the satellites in different orbits? Evaluate the trade-offs between the LEO and GEO for this disaster response satellite, and conclude which orbit type you would recommend. Justify your answer. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, as you can see, as the altitude or radius increases, the orbital time period will increase as t squared is proportional to r cubed. Now, the gravitational force is providing our centripetal force in this case, so F equals gmm over r squared. So this indicates to us that there's a weaker gravitational field at higher altitudes, so the satellites will move more slowly, leading to the longer time period. Now, the LEO has a short time period, so revisits regions frequently, which is good for monitoring rapid events. The LEO provides higher resolution imaging as it's closer, but the GEO provides continuous coverage of one region, which again is useful for real-time responses. The LEO will need more satellites for full coverage, so you need a higher network. So the GEO satellites will also be more expensive to launch as they go into a higher orbit. Now, finally, I would recommend the LEO for frequent global imaging. It's justified by its lower altitude to give better resolution as there's less diffraction and signal delay, and the shorter time period means a quicker revisit, so you'll get more up-to-date information on the disaster. Although more satellites would be needed, the system is possible and the launch costs for each one will be lower. A space agency is evaluating the possibility of constructing a manned research station on a moon orbiting the exoplanet Kepler-62f. The moon has been observed to orbit Kepler-62f with the following parameters. Orbital radius of the moon is 2.5 times 10 to the 8 meters. The orbital period is 1 times 10 to the 6 seconds. The moon itself has a radius of 3.2 times 10 to the 5 meters and a mass of 4.70 times 10 to the 22 kilograms. A spacecraft will need to land on the moon and later escape its gravitational influence to return to Kepler-62f's orbit. Use the moon's orbital radius in period to estimate the mass of Kepler-62f. Calculate the gravitational field strength and the escape velocity at the surface of the moon. Then hence assess whether a conventional chemical lander, capable up to 2.6 kilometers per second, could leave the moon after landing. The agency claims that setting up the station on a moon is low risk in terms of energy requirements for orbiting, landing and leaving. Use your results and understanding of gravitational potential and energy to critically evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one we know m is equal to 4 pi squared r cubed over gt squared. We pop in all the numbers given to us in the question and we can work it out to be 9.3 times 10 to the 24 kilograms. Next one. We know g is equal to g equals gm over r squared to work out the gravitational field strength. So we can work it out when we pop in all the values to be 3.1 newtons per kilogram. We then know that v is going to be equal to the square root of 2gm over r. So we work it all through, pop in all the values, and we get our answer out to be 2.80 kilometers per second. Now, when we compare this with the capacity of 2.6 kilometers per second from the chemical lander, it's not sufficient. So it couldn't actually be greater than the escape velocity we've just previously calculated. So therefore, the standard lander cannot escape. Finally, the energy for orbiting around Kepler-62f is large due to the large orbital radius and host mass. So the landing energy cost is moderate as g is lower than on Earth, but it's not nothing. Now the escape velocity exceeds the capability, so we'll need something else to provide alternative propulsion or fuel. Now the gravitational potential implies a large energy is required to leave, so the conclusion is it's not low risk, especially due to the escape energy. The mission would need a greater propulsion system than the one that it has already. The moon has an orbit around the Earth of radius 3.86 times 10 to the 8 meters with a time period of 2.36 times 10 to the 6 seconds. Using the data provided, show that the product gm is about 4.1 times 10 to the 14 meters cubed seconds to the minus 2, where m is the mass of the Earth. At the surface of the Earth, g is measured to be 9.81 newtons per kilogram. Calculate a value for the radius of the Earth. It has been estimated that at any one time there may be about 1,000 small asteroids orbiting the Earth. These asteroids orbit between 5 to 10 times the distance of the Moon from the Earth. Most make no more than one orbit before being pulled out of this orbit by the Sun. Suggests why these asteroids do not remain in a stable orbit around the Earth. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know omega is equal to 2 pi over t. So it's 2.66 times 10 to the minus 6 radians per second. We know gmm over r squared equals m omega squared r, as the centripetal force is the gravitational force. So at that point, we can work out gm to be equal to omega squared r cubed. Pop in the value, we get 4.07 times 10 to the 14 meters cubed seconds to the minus 2. We know g equals gm over r squared, so r is equal to the square root of gm over g. Pop in all the values, 6.44 times 10 to the 6 meters. Now, the force will vary from the distance of the from the Earth, so according to the inverse square law, F is proportional to 1 over r squared, so the force on these asteroids will be very small. The gravitational potential between the Earth and the Moon due to the combined effect of their gravitational field increases to a maximum value of minus 1.28 megajoules per kilogram at a point between them. Calculate the minimum speed at which a rock would have to leave the Earth in order to reach the Moon. In your calculation, you may assume that the rock has zero kinetic energy when it has a maximum potential energy. The mass of the Earth is 5.97 times 10 to 24 kilograms, and the radius of the Earth is 6,370 kilometers. 4 billion years ago, the Moon had a different orbital period because it was closer to the Earth than it is today. Calculate the period of the Moon's orbit 4 billion years ago when the radius of its orbit was 1.34 times 10 to the 8 meters. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that V is equal to minus gm over r. So you pop in all the values, convert the kilometers into meters, and we get minus 62.5 megajoules per kilogram. The change in gravitational potential is the Moon's gravitational potential minus the Earth's gravitational potential. So we get minus 61.2 megajoules per kilogram. So we know m delta V is equal to the kinetic energy, or a half mv squared. So that tells us, by cancelling out the m's, a half v squared equals 61.2 megajoules per kilogram. So V equals 11,100 meters per second. We also know in this case that the gravitational force is the centripetal force, so gmm over r squared is equal to mv squared over r. So therefore gm over r squared equals v squared over r. We know that v equals 2 pi r over t. So therefore t is equal to t squared is equal to 4 pi squared r cubed over gm. Pop in our values, we get 2.38 times 10 to the 11 seconds squared, square root that, 488,000 seconds, which is 5.7 days. Makemake is a dwarf planet in the solar system. Makemake has a mass of 3.1 times 10 to 21 kilograms and a radius of 715 kilometers. Calculate the gravitational field strength at the surface of Makemake. The average distance of Makemake from the Sun is similar to the average distance of the dwarf planet Pluto from the Sun. A website states that the time taken by Makemake to complete one orbit of the Sun is 20% greater than the time taken by Pluto to complete one orbit of the Sun. Assess the accuracy of the website statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know G is equal to gm over r squared, pop in all the values, and we get 0.404 newtons per kilogram. We know that omega is equal to the square root of gm over r cubed. Pop in all the values, and omega is equal to 6.5 times 10 to the minus 10 radians per second. T is equal to 2 pi over omega, so that equals 9.67 times 10 to the 9 seconds, which is 307 years. So our orbital time ratio between Makemake and Pluto is 1.24. So therefore the orbital time period of Makemake is 24% greater than that of Pluto, so the website statement is not quite accurate. So that brings an end to our revision session today. If we've been successful in our revision session, we can answer A-level physics exam style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So, thank you so much for watching this particular video, which has been on gravitational fields, which is part of AQA A-level physics paper 2. Thank you so much for watching and have a lovely day.